Okay, in this video, we're going to talk about hypothesis testing, specifically one-tailed tests. We'll talk about two-tailed tests in another video, and this is for our binomial distribution specifically. Okay, so let's look at an example. For binomial distribution with a hypothesis test, the first thing we're going to do is state the null and alternative hypotheses, and we'll learn what those are. We are going to decide on the significance level. In this case, the significance level is going to be given to us. But if we were doing this on our own and we were collecting data and doing this, we would decide what significance level we wanted. But this will be given to you. When doing this, and again, we're not going to be the ones collecting the data, but if we were, we need to make sure that we're using a random sampling procedure that ensures the items are independent. Okay? And then we want to conduct the test and interpret the results. So that's kind of the process. What we're going to be focusing on is stating the null and alternative hypothesis and then using the significance level to either reject or fail to reject the null. And so this is important. We are going to reject the null hypothesis, and that's the wording that you're going to use, if the probability found is less than the significance level. Okay? We are going to fail to reject the null hypothesis if the probability found is greater than the significance level. So you have to know these two rules very, very well. All right, let's just jump right into an example. Lenora claims that a die is biased with a tendency to show the number 1. The die was thrown 20 times and the results were as follows. Okay, so she's claiming that this die is going to show 1 more often than it should. We want to use a 5% significance level to test whether Lenora's claim is correct. So the first thing you should do, because we are going to be learning about other distributions throughout this year, so we want to determine that this is a binomial distribution, okay? Because we have a number of times n, so that's our n there. And we need to determine what is the probability of success. So normally on an unbiased die, if I throw it, how many times should I expect 1 to come up? Well, there's 6 sides and there's only 1, so I would expect that it was 1/6 of the time. So this is my n and this is my probability of success. So we've determined that it is a binomial distribution. And so now what I want to do is I want to state the null and alternative hypothesis. So we say h sub 0, that's our null. Okay, and what do we expect that to be? Well, we expect that the probability should be 1/6. The probability of getting a 1 should be 1/6 because that's what it should be if there's no bias. The alternative, and this is how we state that h sub 1, the alternative hypothesis is that the probability is, and we have to look here, greater than or less than 1/6. Well, she's claiming that it's going to show the number 1 more often, so this needs to be greater than 1/6. So that's important. You have to pay attention to what you're told in the problem. Okay, so now that we've got this set up, what we have to do is we have to look at how many times did the 1 actually come up. So that's this information here. The 1 was 6 times it came up when it was thrown. Okay, so what we're going to say is, what is the probability that x is greater than or equal to 6? And we're using greater than because of this, because our alternative was that it was going to be greater than 1/6. So we're saying, what is this actual probability? Okay, and you guys know how to do this. We've reviewed the binomial distribution, so I'm not going to spend the time teaching that. That would make for a really long video. So we can do the probability that x is greater than or equal to 6, which would mean I need to do 6, 7, 8, all the way up to 20. Or we can do the alternative, is 1 minus the probability that x is less than or equal to 5. Okay, so again, we've talked about this. When I do all of this math, using the binomial distribution, I get 0.1018. So if I change this to a percentage, I'm saying the probability that x is greater than or equal to 6 is 10%. Well, that's actually greater than 5%, which is what my significance level was. And since this is greater than 5%, it's greater than the significance level, we're going to say that we fail to reject the null hypothesis. Okay, there is no evidence at 5% significance, at 5% significance level, that the die is biased. Okay, so that's our statement. Lenore's claim is rejected. Okay, but we're going to say we fail to reject the null because everything's going to be based off the null. Okay, so again, I had to determine this, what my probability of success was. I had to state a null hypothesis, which is what we expect the probability to be. This is what we're claiming, or what the alternative is. And then based on this and how many times this one came up, I was finding the probability that x is greater than or equal to 6. And because this probability, this percent, is greater than my significance level, I fail to reject the null. Okay, let's look at another example. A national opinion poll claims that 40% of the electorate would vote for Party R if there were an election tomorrow. A student at a large college suspects that the proportion of young people who would vote for them is lower. She asks 16 fellow students chosen at random from the college roll which party they would vote for. 3 choose Party R. Show at the 10% significance level that this indicates that the reported figure is too high for the young people at the student's college. Okay, so the first thing we're going to do is determine that this is a binomial distribution. And so our number of trials would be 16. She surveyed 16 people. And what we expect is what the national opinion poll claimed, which would be 40%. So that's our probability of success. Okay, so I want you to take a minute and state a null hypothesis and state an alternative hypothesis. And then check your answer with me. Okay, the null hypothesis is what we would expect here. So we would expect 40% because that's what we were told. Now, the alternative hypothesis is that it's either greater than 40% or lower than 40%, and she's claiming that it's lower. So we're going to say the probability is lower than 0.40. Okay, so that's our null and that's our alternative. So now we have to look at how many times or how many people actually chose this party. Well, only 3 people chose this party. So we're going to say, what is the probability that x is less than or equal to 3? And again, I'm using the less than because of this, because she thinks it's low. So what's the probability that x is less than or equal to 3? And I want you to take a minute and I want you to do that math because you know how to do the binomial distribution, and then check your answer with me. Okay, so the answer to this is 0.06514. And if we make that a percent, we get about 6.5%. And 6.5% is less than 10%, which again was the significance level. So when our percentage that we get is less than the significance level, we are going to reject the null hypothesis. And then we're going to make a statement, okay? So at 10% significance level, there is evidence that the reported figure is too high. Let's say for young people at the student's college. And that's just taking the information from here, what they're saying. So we were asked to show at 10% that this indicates that the reported figure is too high for young people at the student's college. So I just took that wording, okay? But you need to make a statement. All right, let's do another one. An advertisement for a dairy spread claims that the spread cannot be distinguished from butter. A worker at the company that produces butter believes this to be false. 10 tasters were chosen and given 2 pieces of bread, 1 with the spread and 1 with the butter. 9 out of 10 tasters identified the butter correctly. And we're going to test at 5% significance level the claims of the advertisement. So again, this is going to be binomial with 10 trials because we had 10 tasters. Now this one you got to be careful because it doesn't tell us what to expect, but I want you to think about this. If this dairy company claims that the spread cannot be distinguished, if they cannot tell the difference between the spread and the butter, then how many times would you expect for someone to get it right? Well, you would expect for them to get it right half the time because they're completely guessing. So they have a 50% chance of getting it right. So we're going to say 1/2. So I want you to take a minute and I want you to state the null and the alternative hypothesis for this. And then check your answer with me. Okay, so the null hypothesis is just that the probability is equal to 1/2. Now this one's a little bit tricky. This should be the probability, and we know we're going to have 1/2, but we have to determine, is it going to be greater than or is it going to be less than? Okay, now if some tasters can identify the butter, then we would expect for this to be higher. So if she's claiming that this is false, that they can tell the difference between the spread and the butter, so we would expect them to get this right more than half the time. Okay, and now we had 9 people out of 10 get it right. So we're going to be testing the probability that X is greater than or equal to 9. Okay, so I want you to take a minute and do that with the binomial distribution and then check your answer with me. Okay, so when we do this, we get 0.01074. And again, if I make that a percent, that's about 1.07%, which is less than 5%, which is my significance level here. So I want you to take another minute and make a statement. Are we accepting? I'm sorry. Okay, so I want you to take another minute and make a statement. Are we rejecting the null or failing to reject the null? And then make a statement. Okay, so remember, when this is less than our significance level, we are going to reject the null hypothesis. Okay, so we're going to make a statement. At 5% significance, at 5% significance level, there is evidence that the proportion of people who can distinguish the butter is more than 1/2. Okay? And you can have a little bit different wording, but you need to make a statement based on the concept here. Okay, the last thing we're going to talk about in this video is critical regions or rejection regions. And we have a critical value, and that's the value at which you change from accepting the null hypothesis to rejecting it. Okay, so that's going to be based on our significance level. At what point, what number do you change from accepting the null or failing to reject the null to rejecting it? Okay? The critical region or rejection region is the range of values written as an inequality for which you reject the null hypothesis. Okay, so let's look at an example for this. Worldwide, 25% of men are colorblind, but it is believed that the condition is less widespread among a group of remote hill tribes. An anthropologist plans to test this by sending field workers to visit villages in that area. In each village, 30 men are to be tested for color blindness. Find the rejection region for the test at 5% significance level. So instead of telling us how many people were colorblind and us testing this to determine if we should reject or fail to reject, we just want to know what's the rejection region. At what number of people would we either fail to reject or choose to reject the null? So we're still going to write our distribution. This is a binomial distribution. They chose 30 people to test, and we expect that 25% of them will be colorblind, so 0.25. Remember that we're doing this at 5% significance level. That's important to keep in mind. So what we want is we still want to state our null hypothesis. You're always going to do that. So our probability we expect to be 0.25. Our alternative hypothesis is that the probability is less than 0.25 because they expect that less people in this area, or they believe that less people are colorblind. So this is our null and alternative hypothesis. So what you want to look at now is we want to find the probability that X is less than or equal to some value. So normally we would test a value, right? But we don't know what that value is. So the probability that X is less than or equal to some value K is less than 0.05, because if it's less than our 5% significance, then we are going to reject the null, and that would be the rejection region. So this can get kind of tedious, okay, but what you're going to be doing is you're going to say, what is the probability that x is less than or equal to 1? You could even start out with 0. What is the probability that x is 0? But what is the probability that x is less than or equal to 1? What is the probability that x is less than or equal to 2? What is the probability that x is less than or equal to 3? And you're going to do that until it changes. So I'm going to show you what I mean. You can actually find those two values, but if I do this probability that x is less than or equal to 3 here, which would be 0 plus 1 plus 2, I get 0.0374. This is less than 0.05. This is less than 0.05. But if I go to the probability that x is less than or equal to 4, which would be 0, 1, 2, 3, and 4, I get 0.0978, and that's greater than 0.05. So in between these two numbers is where that changes from me rejecting the null and failing to reject the null. So what we would say is the rejection region is going to be when x is less than or equal to 3. Any number 3 or lower, these here, is going to cause me to reject the null. But I would fail to reject the null when x is greater than or equal to 4. So if it's 3 or less, I'm in the rejection region. So they didn't give us a value to test, but by knowing this rejection region, I can say, after they've tested the people, if they had 3 or less, we're going to reject the null, okay? The null is not true. The alternative hypothesis would be accepted in that case, but we would say fail to reject the null. But if it's 4 or greater, if they test people and they get 4 or greater, then we're failing to reject the null, okay? All right, so we're going to look at one more example of this. And this is the example from the beginning. Lenora claims that a die is biased with a tendency to show the number 1. And the die was thrown 20 times. But now, instead of having values, how many times a 1 came up, we're just going to find the rejection region at 5% significance. So again, we're going to state the binomial distribution. We have 20 trials. And we talked about this. I would expect a dice to get the number 1 out of 6 times, or 1/6 of the time, because there's 6 faces and there's only one number 1. So 1/6 goes here. Okay, and now we can state the null and alternative, which we've done this because this was a previous example. The probability is 1/6 for our null hypothesis. And for our alternative hypothesis, because she's saying it's biased towards 1, we would expect that that would be more than 1/6. Okay, so now what we want to do is we want to find the probability that x is greater than or equal to some value k, and that is less than the 0.05, because that's our significance level. So what value, the probability that x is greater than or equal to some value, gives us a probability less than 0.05. Now I want to show you an alternative to this. You can do this, but because this is greater than, you're going to be looking for like 19 and 20, the probability that x is greater than 19, or the probability that x is greater than or equal to 18, or greater than or equal to 17. And that's actually working from the top down, because if you start from 0 here and 0 to 1 and 2 to 3, it's not going to work out for you because we're doing greater than, and you're going to be going a long way. So I want you to think about the alternative. I can find that, or I can say the probability that x is less than or equal to some value of k needs to be greater than 0.95%, or 95%, which is 0.95. And I want you to think about this on a number line. Let's just pick a number 5 and then 4. If I find that the probability that x is greater than or equal to 5 is less than 5%, okay, so think like 0.04, if it's less than 5%, then the probability that x is less than or equal to 4 has to be more than 95%, because 95 plus 5 adds up to your 100% probability, or your 1 if you're doing the decimals. So if you think about it this way, if I don't want to find this, if this is challenging for me, then I can do this instead. The probability that x is less than or equal to some k has to be greater than the 0.95. And so what I would be doing here is I would find the probability that x is equal to 0. And then I'd find the probability that x is less than or equal to 1. And I would do that 2, 3, 4. And I want to show you, we're going to get all the way up and you're going to have to go a little ways. When we get the probability that x is less than or equal to 5, I get 0.898. And so what you see here is that between these two is where it changed. This one was less than 0.95 and this one was greater than 0.95. So I need to think about my alternative. If the probability that x is less than or equal to 6 is greater than 0.95, then the probability that x is greater than or equal to 7 must be less than 0.05. Okay, so that's the alternative to this. And so this is my rejection region. If I started this one and had to work my way down, I would have had to go 20, 19, 18, and the sums of all of those, and that would have took me a long time to get to 7. So this way was quicker, okay, with the less than or equal to. So you just have to understand the alternatives. So this is my rejection region, and my critical value is 7, okay, because that's where it changes. So if I roll the dice and it shows 1 more than 7 times, then I'm going to reject the null. But if it shows it less than 7 times, then I'm going to fail to reject the null. Okay? All right, we will look at this more in class. Review what you need to. Make sure you kind of understand this concept as best you can, but we will practice this in class. Okay?